Hi everybody, very good morning. So I hope you're doing great, and it was a holy season, and I hope. But yeah, generally, in Chennai doesn't have that much of happenings to Holi. Still, okay. Right. So today is supposed to be your question paper discussion, isn't it? So how was the test? Was it fine? Difficult? Easy? Okay. Fine. Let me share my screen. Just discuss the question paper. One second, before sharing, I'll just download the question paper. Just give me one moment. Now I can share the screen. Yeah, so I think this was your question paper, right? Okay. So first question, right? The molar conductivity of 0.1 m 630 over H is this much, right? I think it's given as wrong. It should be 4.6 Simon centimeter squared per mole. Only centimeter squared per mole is given, right? Do you know what is the unit for molar conductivity? The telling molar conductivity of this much solution is this much. That is 4.6 Simon centimeter squared per mole. It should have been, right? But still it's okay, right? Now they're asking what is the conductivity and what is the resistivity, right? Okay. Now we have one equation for lambda, right? Lambda m is equal to k divided by c. This is the equation which we use, right? But again, if at all you want k value in Simon per centimeter, and if lambda value is in Simon centimeter squared per mole, right? What we need to do, we need to multiply the numerator by 1000. Isn't it? I hope this was the now this is the formula is in terms of Simon meter squared per mole, right? If this is now Simon meter squared per mole and K will be in terms of Simon per meter, right? Then you have the concentration in terms of molarity. In this case, you have to put 1000 in the denominator. Please remember these two formulas, very, very important, right? So this time they have given the lambda m value in terms of Simon centimeter squared per mole, right? So you will get the K value in terms of Simon per centimeter. If obviously the C value should be the molarity, that is 0.1. Okay, so for this question, what we do, we get lambda m is equal to K, or lambda m value is given to us. What is it? Lambda m value is 4.6, right? Divided by K. What is K? K is something but a conductivity, kappa, right? Right. So K is your conductivity, and then we have the concentration. Concentration is 0.1 m, and I told you have to put 1000 in the numerator. That also should be done, right? So you will be getting 0.46 divided by 1000, or we can write it as 4.6 into 10 to the power minus 4 Simon per centimeter. This is your K value, right? Your K value is, that is, you have found one of the things. They wanted to find the conductivity. Conductivity value is 4.6 into 10 to the power minus 4 Simon per centimeter. Now, okay, and they wanted to find the resistivity also. right? Resistivity is what? Resistivity and conductivity are? Any idea how to find resistivity, people?
Inversely proportional.
Inversely proportional, like you can just say that they are reciprocal of each other, right? So conductivity and resistivity, right? So you know the conductivity value now, you can find the resistivity. So resistivity, let me put it as rho. That's what you use, right? For resistivity, you use rho. Rho is equal to 1 by K, right? So you have 1 divided by 4.6 into 10 to the power minus 4 Simon per centimeter. Now in this case, you will be getting what? You will be getting ohm meter. Don't mess up with the units, right? Resistivity unit is what? Ohm meter. Conductivity unit is per ohm per meter. That is why it became Simon per meter. Remember that. I mean, if at all you write here, it should be ohm centimeter, because we have K in terms of Simon per centimeter. So in this question, you should be getting the unit as ohm centimeter, right? You should be writing the units also, or else they'll cut marks. Be very careful. Okay, right? Fine. That's about the first question. I hope everybody understood. Okay, next. The conductivity of metal decreases. Okay, the conductivity of metal decreases while that of electrolytes increases with increase in temperature. Ooh, okay, they're asking why. It's a very good question, is it not? Like, first of all, I don't know whether you know this, right? Say if there is a metal, right? If there is a metal and I increase the temperature of the metal, right? Say I go from 25 degrees Celsius to 35 degrees Celsius, right? What will you see is that the conductivity value is going to become poor conductor of electricity, in the sense that if it was a very good conductor, now it would not be that good conductor of electricity if I increase the temperature, right? But in the case of electrolytes, right? Let's say when you know, right? Whenever we say conductors, right? Whenever we say conductors, right? We can have two different types. One are what are called as electronic conductors. The other one is what is called as electrolytic conductors, right? Okay, electronic conductors are nothing but metallic conductors, right? The only difference between these two is that the charge carriers here are free electrons, and then here the charge carriers are what? Ions, right? So what are they telling here? Here, if I increase the temperature, K value decreases. If I increase the temperature here, the K value increases. That is what they're telling, right? Okay, now why is it happening? Now, what we need to understand is, in case of electronic conductors, right? In case of electronic conductors, as temperature increases, resistance increases. Okay, as temperature increases, resistance increases. Obviously, if the resistance increases, the conductivity will decrease. As simple as that. Okay, as temperature increases, resistance increases, and that's why you see that the conductivity decreases. All right. Okay. Now, when I go to electrolytic solutions, now what we need to understand, it is all about ions, right? And now I can say that I can put it this way. I can say, just give me one moment. Right. So we have ions. Obviously, the ions, these ions has to move, right? This ion has to move. They'll be carrying this charge, and that is they are the charge carriers, and that is what is responsible for these kind of electrolytes to be conductors, isn't it? Right. So when I increase the temperature, right? When I increase the temperature, what is going to happen? Say now the ions will move faster, isn't it? That makes sense, because they will absorb the energy. They already have some kinetic energy. They will absorb the heat also. So that will be converted into kinetic energy, because they will be moving very fast. Right? That makes sense, hopefully. Right? So when the ions move faster, or in a little more technically, since we are science students, like since we speak a little more technically, I can say that if temperature increases, the ionic mobility, right? The ionic mobility increases. Ionic mobility is nothing but the ability of the ion to move, to be a mobile species, right? And obviously, more and more is the ionic mobility, more and more will be the increase in conductivity also, right? So as temperature increases, the kinetic energy of ion increases, the ionic mobility increases, and that's why the conductivity also increases, right? Okay, so that is how you answer these questions. All right. Okay, next. Yeah. What is that? Write the IUPAC name and draw the structure of the coordination entities. Basically, whatever is inside the bracket, right? Whatever is inside the square bracket, that is what is called as a coordination entity. All right. Okay. I have to write the IUPAC name and the structure, basically. Very simple. You will see how many ligands are there totally. You have coordination number is 6, right? The moment coordination number is 6, right? And yes, we'll write the compound now. So we have PT, Cl, NH3, 5 times, and then we have CO2. Right? Okay. Now we know what are the rules which you have to follow. We have to name the cation first and then only the anion. In this case, the coordination sphere itself is the cation, because we know that only we write first, then we write the anion. Right? Okay. Now we have to name the coordination sphere first, that we understood. And whenever we go for inside the coordination sphere, we have to name the ligands first. Right? So again, we have two different ligands. This is chlorido. This is amine. Right, so obviously alphabetical order, A comes first. So we have 5 such this thing. So we write penta, amine, and only 1 chlorine is there. So chlorido, right? And then we have platinum, right? So platinum, we have to find the oxidation state, and then we have to write it in this thing that we can find. Say if platinum is X, for Cl it is -1. For ammonia it is 0, because ammonia is a neutral ligand. Right? If you remove this 3 Cls, right? Basically, if you remove this 3 Cls, I'll be able to write like this, right? PT, Cl, NH3, 5 times, right? 3 plus. Why 3 plus? Because 3 Cl minus ions are removed. So plus 3 Cl minus would have come. Only if you mix these two, the overall complex would become neutral. Right? So immediately understand that the charge on the coordination sphere is actually going to be 3 plus. Right? Okay. So X minus 1 should be equal to plus 3. Right, so if this goes here, X is going to be in +4 oxidation state, and we know we should write in Roman numbers. So 4 we write, and then outside what we have? Outside we have chloride. That's it. This is the name for this compound: pentamine, chlorido, platinum 4, chloride. Right, and structure is very easy. Right, structure is very easy. So we need to have octahedral shape like this. So we have 1 chlorine. All the others are ammonia. This is what is your octahedral shape. Very simple. Right. Okay. Next question. Right. So if not understand, please stop me right there and ask. I'll explain you one more time. Right. Please don't sit now. Okay. Next. So this is done. Oh. Okay. Okay. This is a different compound. I think you should be able to do it this time. But again, I will just write the IUPAC name of this. Okay. We have. Okay. I write it. Okay, what we have? PT, Cl, CH, 2 NH2. That's what we have, right? NH2, CH3. Sorry, CH3, NH2. Okay, doesn't matter, whatever it is. Okay, CH3, NH2. And then we have NH3 twice and Cl. Okay, we need to write the IUPAC name of this. Fine. So this is the only difference is that here the ligands are different. Right? How do you call this ligand? CH3 and H2. Any idea? Any idea? CH3 and H2. What is the actual name of what is the IUPAC name of this compound if I take?
Methylamine, sir.
Methylamine, right? So that is what you have to use here also. But instead of 1 M, you should write 2 M's. That's the only thing. Okay, right? Fine. So, right. So again, this is amine, this is methanamine, this is chlorido. So obviously you have to write the chlorine, amine first because alphabetical order. Right? Again, this is your positive, this is your negative, and you easily understand the total positive is plus. Here only 1 Cl is there, so 1 Cl minus. That is how they'll dissociate. Right? Okay, so here we will have first diamine, and then we have chlorido, and then we have methanamine, double M you have to put, right? Methanamine, then we have platinum, right? And then we have to calculate the oxidation state. So X, For this, it is -1. Okay, and the overall charge is +1. So you'll find X to be in +2 oxygen state. So platinum here is going to be in +2 oxygen state, and outside we have what? Outside we have the chloride. That's it. This is the name of the compound. Right? Okay. Next question. What is there? Okay, you have to find using crystal field theory, write the electronic configuration of ion in the following complex ion, also predict its magnetic behavior. That is very simple. Okay, we're using this only, right? Oh, I'm so sorry. This question. Okay. So compare the magnetic behavior of the complex entities FeC and 6 times with 4 minus and F6 3 minus. Right? Now we know what you have to do. You have to go for, right? You have to go for finding the, see, they didn't mention whether you have to use VBT or whether you have to use crystal field theory, right? They didn't say anything, but I would say it is better to go with VBT. Right? It is better to go with VBT because there you will get a little more easier picture. But in the next question they have mentioned you have to use crystal field theory only, right? Okay. Anyways, for this question we use VBT, right? For FeC and 6 times 4 now minus, and FeF6 3 minus. For both of them we'll use VBT to find your magnetic behavior. All right. Okay. So we'll do that. So the first we'll do for FeCN 6 times what? 4 minus or 3 minus? 4 minus. Excuse me. Right. So first, we need to understand that Cn minus is there. Cn minus is going to be a strong field ligand, right? And whenever we know we have a strong field ligand, forced pairing will happen, isn't it not? Right? The electrons, the unpaired electrons, will be forced to get paired. All right. Okay. Now here we have to calculate Fe is in which oxidation state. So X for Fe, and so you have 6 Cn minus. So 6 will come is equal to -4. So definitely X is going to be in +2 oxidation state. So we have Fe2 plus ion. Okay. Right. So we need to know what is the atomic numbers, at least the oxidation state, I mean the valence electronic configuration, everything we need to know, or else you'll not be able to answer these kind of questions, right? So we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, iron. Okay. Right. So it's the Fe, right? Fe2. Okay, right. That's what it would have been for Fe, the valence electronic configuration. Okay. For Fe2 plus, right? All that we need to do is remove the 2 electrons. So we would have had 3d6, 4s0, 4p0, and 4d0 because we know the p orbital will be there, d orbital will be there, but it will be empty. Okay, right. So we know how d6 we should write, is it not? Okay, this is 4, 1, 2, 3, 4, 5, 6, and this is okay. This is your 3d. This is your 4s, this is your 4p, and we would have had your 4d also, no issues, right? Now this is in the absence of the ligand, right? This particular configuration will be there in the absence of the ligand. But now when the ligand is present, right? When the ligand is present, what is going to happen? Because it's a strong field ligand Cn minus, right? You'll go for forced pairing. So all the unpaired electrons here, right, will get paired, and then you would have had, right? You would have had 1, 2, 3, 4, 5, 6. That's it, right? And then you have 4s, and then you have 4p, and then you would have 4d. So now, if you see the hybridization also, it would have been what? It would have been d2 sp3. It would have been the hybridization. Anyways, now you understood that there are literally no unpaired electrons. Is it not? All the electrons are paired. So you can easily say that this particular species is going to be a diamagnetic species. Right, this particular species is going to be a diamagnetic species because it doesn't have any unpaired electrons. Right, now you can do the same way for your F6 3 minus also, right? Except that in this case I think it is going to be Fe3 plus, right? Fe3 plus would have had 1 electron, 3 unpaired electrons will be there, so definitely it is going to be a paramagnetic species. That F6 3 minus would have been a paramagnetic species, right? Okay. Next question. Okay. Now, using crystal field theory, you have to write the electronic configuration of ion and also predict its magnetic behavior. Okay, that's very simple, right? So this one is very simple. So we have Fe2 plus if you check, right? Now Fe2 plus, we know it is going to have 3d6 configuration. And look at what kind of ligand I have. I have H2 as the ligand. H2O, we consider them to be weak field ligands, right? We consider them to be weak field ligands, right? So again, here pairing will not happen. That's what you need to understand. Strong field ligands are there, pairing will happen. If weak field ligands are there, pairing will not happen. So we know how to write this, right? We have T2G, EG, and in T2G, we know we have 3 orbitals, EG has 2 orbitals. We account for 6 electrons, 1, 2, 3, 4, 5. Now, if it was some other thing, we would have done pairing here itself. If it was some other strong field ligand, we would have put these 2 electrons here and here, right? But since it is weak field, we go for higher energy orbitals. Okay, so then 1 more electron will come here. Done? Okay. Now you can easily understand how many unpaired electrons we have. We have 4 unpaired electrons, so definitely it is going to be a paramagnetic species. And you can also find your magnetic moment mu, right? Root of 4 into 4 plus 2, right? Root of n into n plus 2, root of 4 into 4 plus 2 will become 4 into 6, root of 24 Bohr magneton. What is that? Magnetic moment value, right? Okay, so that is about your FeH2O 6 times 2 plus. Okay, next one, write the IUPAC name of this. Okay, we can do that, IUPAC name. So you have CO, Cl2, and twice NO3. Okay, we do it here, right? So we have CO, Cl2. So this should be E. Okay, first, how do you write the name of this En? En is nothing but this one, right? En is nothing but NH2, CH2, CH2, NH2. Is it not? This is what is your En. That's what we write in short form. So how do you write the IUPAC name of this ligand? The IUPAC name of the ligand is ethane 1,2 diamine. That's how we write. Is it not? Ethane 1,2 diamine. Okay, right. So that if it's done, then that is very easy. Okay. So we again the coordination sphere is only going to be the positive charge. The counter ion is going to be negative charge. So we have to write the coordination sphere. I mean, name the coordination sphere first, then go for your anion. Right. So we will have okay, first a dichloride, right, and then for your En twice is there, and you understand that there is going to be a didentate ligand. Whenever we have monodentate ligand, we can use bi, di, tri, tetra, all those things, right? But if it is going to be a didentate ligand, we have to use bis, tis, tetris, and so on and so forth. So for this case, you have to use that. So it is going to be bis, ethane, 1,2 diamine, right? Diamine. Okay. Then we have your cobalt. You can calculate the oxidation state. I think it will be X minus 2 equal to minus 1 plus 1, because NO3 minus will go out and it will become plus. So you have X is equal to plus 3. Right? So cobalt is in plus 3 oxidation state, and outside we have NO3. Okay, right? Fine. Next, predict the geometry of this. Again, when I have coordination number 4, right? When we have coordination number 4, we need to understand that there are two possibilities. One, it can be a square planar complex, or it can be a tetrahedral complex. And how do you decide that, people? How do you decide that it is going to be a square planar or tetrahedral? How do you decide that? Nobody knows. We did so many questions, right? How do you decide that? When I have coordination number 4, how do we decide whether it is going to be a square planar or tetrahedral? How do you decide that?
We have to first use VBT, no, sir. And then
Okay.
after pairing, we have to check if it's DSP2 or SP.
Okay, depending on the hybridization. Isn't it?
Yes, sir.
Right. So what hybridization with shape?
SP3 is tetrahedral.
Okay.
And DSP2 is square planar.
Good. Right. This is how we decide. Right. So whatever we did for this one, Fe2 plus what we did, the same thing we have to do for this one also. So we have Ni, Cn 4 times, is it 2 minus? Yeah, 2 minus, right? Now we understand that here I have a strong field ligand, so definitely pairing will happen, right? So if I look into this, okay, we have nickel in +2 oxidation state, right? Yeah, nickel in +2 oxidation state, right? So nickel +2, like basically, if you check nickel, cobalt, nickel, iron, cobalt, nickel, 3D8 will come, right? So it is 3D8 for S2. Now if it is Ni2 plus, all that we have is 3D8 for S0, 4P0, 4D0, right? So if I just draw 1, 2, 3, 4, 5, 6, 7, 8, right? And 4 is nothing, 4P nothing. So whenever we have this, what is that, strong field ligand, we know pairing will happen, right? Now instantly these two unpaired electrons will get paired. 1, 2, 3, 4, 5, 6, 7, 8. And then we have 4s. Oops, so sorry. This is 4p. Okay, and we have the 4d also. Right? Okay, now we can easily understand that you can easily form what? You can easily form DSP1, P2. Right? You can easily form DSP2 hybridization, and whenever we have DSP2, it is going to be square. Right? Very simple. Okay, that is done. Predict the geometry of this. This geometry is square pair. Okay. Right. Next, calculate the spin only magnetic moment. Basically, you have to find the mu value. Right. Again, what you have to do? All that you have to do is go for NH3. NH3 is a strong field ligand. Same, exactly same thing. What we did case of this thing. You know, for copper, it would have been 3D 3D9 4s2. Right, and it is copper 2 plus, so it would have been 3D7. Right, so for 3D7, ammonia is a strong field ligand, right? Maybe we can just do it somewhere. So when you have 3D7, 1, 2, 3, 4, okay, 1, 2, 3, 4, 5, 6, 7. Okay, now ammonia is a strong field ligand, so pairing will happen. Okay, 1, 2, 3, 4, 5, 6, 7. This is how the pairing will happen, right? But what you are seeing that there are one unpaired electron because ammonia is a strong field ligand. One unpaired electron, so it would have been root of 1 into 1 plus 2, that will be root 3 Bohr magneton should be the answer to this question. Okay, because strong field ligand is there, so pairing will happen. If at all you see that there are 3 unpaired electrons and you directly write it, it's going to be wrong. Be very careful. You must always go for this and go for pairing if it is strong field ligand, and then calculate your what is that? Your magnetic moment values. Okay, right. So next question. Okay, give names of two. Okay, I think this was not there in the syllabus, I guess, right? Application of coordination compounds. Do you have in the syllabus? Okay, even I'm not sure. Like if at all, I remember one thing. One thing is cisplatin. Right, cisplatin is actually used in cancer therapy. Okay, and there are various other things, but nothing comes to my mind such. I don't have to worry about it. I think this is not there in the syllabus. Okay, the application part. Okay, next. Okay, it's a similar thing. NiCN, the same. This thing which is here, we have already done. Valence 1 theory, explain the geometry, magnetic behavior, everything we have done. Okay, very simple. Okay, next. CO is a stronger complexing reagent than ammonia. There are other states. I to give reasons for this. Okay. Right. So they're telling basically what they're telling. Basically, CO is a stronger ligand than NH3. They're asking you why. Right. Now, if you study your metal carbons very carefully, right? CO is capable of forming both sigma as well as pi bonds with a metal. Is it not? Hope you remember that. Excuse me. Right. So we can have a double bond between your carbon and the metal in case of double this thing, because this would have been a bond like this, that is a sigma bond, coming from a coordinate bond, electron coming from carbon donated to the metal, right? And I can have a pi bond going from the electron going from metal to carbon. We have discussed this in detail in metal carbonates, right? In your book also it is there. You can check it, right? So CO is capable of both forming sigma bond and pi bond to the metal, but ammonia is not like that. Ammonia can form only sigma bond. Right? Ammonia can form only sigma bond. It can donate electron to the metal, but it will not be able to accept electron from the metal. And that's why it is a weaker ligand and CO is a strong field ligand. That's how you answer these questions. Okay, fine. The molecular shape of NiCO 4 times is not the same as that of NiCN twice. NiCN this. Okay, right. For NiCN 4 times, what we got? We got DsP2, right? It is square planar, right? For NiCO, what is going to happen? Now, Ni, the only difference between Ni, this one, and NiCO 4 times, here nickel is going to be in zero oxidation state because CO is a neutral ligand. That's the only difference here, right? Okay. Now, if it is going to be 3D8, 3D8 4s2, isn't it? Right. So we have, this is going to be 3D8 4s2. So what is going to happen? We will have one, okay. We'll have 2 electrons here, then 8 electrons like this. Okay. Now, even if you go for pairing, right? Even if you go for, obviously, CO is a strong field ligand. I will go for pairing, no doubt. 1, 2, 3, 4, 5, 6, 7, 8. Now you have this electron also, right? These two will also be shifted to this. Right. Now what is remaining? Right, this is your 4s, right? This is your 4p. So only way you will be able to make 4 hybrid orbitals is when you take s, p1, p2, p3 hybridization, right? But even though there's a strong field ligand, what do you understand here? Here we have pairing happening in a little different way. The 4s electrons shifted, these two are getting paired. So eventually the available orbitals are only going to be sp3. But in this case, you saw it is going to be dsp2, it is square planar, and definitely this is going to be tetrahedral. Right? That is why there is a difference in shape. Okay, I hope that makes sense. All right. Next question. Right. Okay. Suggest reagent to bring about the following conversion: hexane 1-all to hexanol. It's very easy, right? What we have is basically alcohol to this thing. What do we need to use? What is the reagent here? Quick. What is it? Hexane 1-all, CH3, CH2, CH2, CH2. How many? 1, 2, 3, 4, 5, 6 OH. This is what is the hexane 1-all. What do you have to do? You have to convert this into CHO. What do you need to do? What is the reagent used? This is oxidation, isn't it? Alcohol to your aldehyde is oxidation, right? And if I go for a very strong oxidizing agent, I know this part will convert it into COOH. For example, if I put KMnO4, definitely this part will convert it into acid part, right? But if at all yes, any answers? Okay. If at all I want to convert this into this, that is CHO, we need to use a mild oxidizing agent. And any guesses what we have to use? Really? Okay. We need to use PCC. That's it. Pyridinium chlorochromate. This is a mild oxidizing agent which will convert your alcohol to aldehyde only. Right? Okay. For this, the first one, the answer is PCC. Pyridinium chlorochromate. Okay. Fine. Next, you have to convert cyclohexanol to cyclohexanone, double bond O. So all that we need to do is again oxidation. Alcohol getting converted into ketone, because in this case it's a secondary alcohol. Secondary alcohol will always get to ketone. This is the primary alcohol to aldehyde. Right now, here also you can use PCC. Right, no issues. But in this case, you can even go for KMnO4. There is no problem here because secondary alcohols will not give acids. They will not be able to further oxidize to give acids. So in this case, you can use PCC or KMnO4. Both are correct answers. Right. Okay, next. We have 4-fluorotoluene to 4-fluorobenzaldehyde. Look at this. What we have toluene, 4th position fluoro, obviously 1, 2, 3, 4. 2, we need to convert this into CHO with F like this. Yes. Any idea what to do here?
So we can use CrO3 here.
CrO3, correct. What reaction is this? It's not CrO3. We do the little, like say, similar reagent to that. What is it?
Sir, chromyl chloride.
Correct. Okay, chromyl chloride. What is the formula? CrO2Cl2. This is what is the formula for chromyl chloride. Okay, what reaction is this? Is the name reaction, right? What reaction is this? This is a name reaction. What name it has?
I think Ettard reaction.
Right. Ettard reaction. Right. It's Ettard reaction where you convert directly a toluene, whatever, using chromyl chloride as the reagent. Okay. Right. Good. Fine. Next one we have is ethane nitrile to ethanol. Okay, we'll do that. What is it? Okay. Ethane nitrile is very simple. Ethane nitrile is nothing but CH3, C triple bond N, and they want you to convert it into CH3CHO. What is it? Cyanides to this thing. What is that? Aldehydes. Again, a very famous name reaction. What name reaction is this? We have
Dibal, sir.
what is it?
We use dibal for this.
Dibal H. No. Dibal H.
Plus HCl.
Sorry. Come again.
Stannous chloride plus HCl.
You don't have to go for stannous chloride. We can just use SN bar HCl. Tin in the presence of HCl. That's it. This is enough. This is a very famous name reaction. What name reaction is this?
Stephen.
Yes. Stephen's reduction. Right? Okay. Rohan, you can use dibal H, but not directly. If I go for hydrolysis of this, right? If I go for hydrolysis of this, I will be getting CH3COOH. Then you can use your dibal H to convert this into your aldehyde.
So you can't use it directly, sir.
No, we cannot use directly. If you use dibal H directly, I don't think anything will happen. But if at all you use normal reducing agent, say if you go for H2 bar nickel, right? You will be actually getting amine, CH3, CH2, NH2. That you will be getting. Like we didn't see amines. I don't know. Raghav say anything to you guys regarding this chapter, amines?
No, sir, I don't think so.
I'll speak to him again. Like he told some weekday we can have, but again, after that, no information came. I'll speak to him again. Okay. Right. So, and anyways, directly you can use SN bar HCl, Stephen's reduction. If at all you want to go for a little, one more step, go for hydrolysis, then use dibal H, that is a reducing agent to form this. That's also okay. Okay. But in this case, I think they don't want this. They want to do it in one step. That's why they're asking, what is the reagent which you have to use? That's the question. The reagent you have to use is SN bar HCl. Right? Okay. That's good. That's question is done. Then we have short notes on Rosenman reduction. Okay. Rosenman reduction is what? RCOCl getting converted. We are what we have to use here? H2 in the presence of palladium poisoned with BaSO4. Right? You have to tell you to write the reaction and tell them that acid chlorides can be converted into your aldehyde using this H2 in the presence of palladium poisoned with BaSO4. Write this in words and done. You're done. You'll be getting the marks. Right? Write the reaction, give an example, and then write the same reaction in terms of words. Done. That's what is going to happen. Right? Okay, next, Cannizzaro reaction, very famous reaction. There again, just you tell that it is, what is that? Disproportionation reaction. One will get oxidized, the same will get reduced. The reagent used is NaOH, concentrated NaOH, and you take an example and you have to tell that this reaction will happen only if I have, or only if I don't have dash. What should I not have in the compound? For anything to undergo Cannizzaro reaction, what should I not have in the compound?
Alpha hydrogen.
Good, right? So because the reagent we use is NaOH, right? Now NaOH is actually used in aldol condensation also. It is used in your Cannizzaro also. What is the basic difference? We need to have carbonyl compounds having no alpha hydrogen. Then it is Cannizzaro. If it is having alpha hydrogen, aldol condensation will happen, right? Okay. So now this we can easily say this is a disproportionation reaction. This CHO will get oxidized to COO minus or CO minus or COH also we can write, not a big deal. And then it will get reduced also to form CH2 of HCHO. Formaldehyde also you can take. It will get oxidized to HCO minus and CH3OH. That also is fine. Okay. Right. Next, acetic acid can be halogenated in the presence of red phosphorus and chlorine, but formic acid cannot be halogenated in the same way. Why? Okay. What reaction are they talking about? Any clue? Guys, look at the question. Acetic acid can be halogenated. They didn't say where. How is it happening? How is it happening? They're telling in the presence of your red phosphorus and chlorine, right? But formic acid cannot be halogenated by this way. If you use red phosphorus in the presence of chlorine, that is not possible. What reaction are they talking about? So maybe if I write the reaction, you will be having an idea. So we have acetic acid, CH3COOH, and we are writing red phosphorus and we have Cl2, right? The product would be CH2Cl COOH. What reaction is this?
So this is halogenation, right?
Yeah, halogenation, obviously. There is a name reaction for this. There is a name reaction. I'll give you 10 seconds to think about it. Okay, it is what? It is HVZ reaction, and we know the full form also. Hell, Volhard, Zelinsky reaction, right? That's a famous named reaction again, right? So what you understand is for this reaction to happen, I need to have alpha hydrogen present, right? What are they asking? We have HCOOH. Obviously, if you put red phosphorus in the presence of chlorine, nothing will happen because it contains no alpha hydrogen. That's the simple answer to this question. Okay, right? For HVZ reaction to happen, we need to have at least one alpha hydrogen in the acid. Because alpha portion only will get halogenated. It is not normal halogenation, right? See, same thing. If I put SOCl2, what will happen? If I have CH3OH and if I put SOCl2, what will happen? You have to revise, people. You have to revise. This is not good. That too, the exams are very nearby and you're not able to answer this simple question is very scary. Okay, be very careful. This is normal. You will be able to convert them into your acid chloride. That is a different reaction, right? This is also halogenation, right? This is converting your acid into an acid chloride. This is different. This is also halogenation, but halogenation happening at the alpha position. Right, this reaction will be given by your HCOOH also, right? Is it not? Say if I take HCOOH, right? And I put SOCl2, right? What I'll be getting? I'll be getting HC double bond O Cl. That's what you'll be getting. Right? This is your formyl chloride, if you want to keep it like that. Right? This reaction is possible for HCOH also and CH3COH also, but in this case, there's no alpha hydrogen, so HV reaction is not possible. Okay, right. I hope that makes sense. Right? You have to revise the reaction, people. This is not the way. It shouldn't be like this. Okay. Next, write down the functional isomers of the carbonyl compound of the molecular formula C3H6O. Okay, we have to write all the functional isomers, only functional isomers. Basically, for this compound, you can easily see you can have either an aldehyde or a ketone. That's what you can have. Okay. Which isomer will react faster with HCN and Y? Okay. Now, when we have your aldehyde and ketone, right? Which reacts fast? Okay. First, there are a lot of questions asked here, right? Explain the mechanism of the reaction also. Okay. Will the reaction lead to a completion with the conversion of the whole reactant into the product at reaction conditions? Yeah. Okay. Fine. If a strong acid is added to the reaction mixture, what will be the effect on the concentration of product and Y? Okay, there are a lot of these things to think about. Right. Fine. So first look at the mechanism. What exactly is happening? Right. So we have a C double bond O, right? And we have HCN. Whether it's ketone or aldehyde, we'll come back to that later. Right? We'll try to answer the other questions. Right? So we have HCN we're adding. Right? Now tell me, people, what kind of reaction is this? What is the type of reaction? Let's say we have I don't know, nucleophilic substitution, reduction, oxidation, like that. What reaction is this? What is the type of reaction here?
Nucleophilic addition.
Good, right? It is nucleophilic addition, right? Now, why do we call it as nucleophilic addition? Because from this, your Cn minus comes, right? And we understand that there's a del positive here, del negative here, right? So now what is going to happen? This Cn minus will go attack this particular carbon, and obviously the double bond breaks, right? So we would have had CO minus, we have a Cn and two more bonds, obviously, depending on the aldehyde of ketone, right? And obviously we have H plus, right? And that H plus will be taken up by this O minus, and then we have OH, Cn like this. Okay. Now, what we need to understand is this reaction will not go for complete conversion, right? Will not go for complete conversion, right? Why? They're asking you this question. They're asking, will what they're asking? Yeah. What is that? Will the reaction lead to completion with the conversion of the whole reactant and product? No. The answer is no. It will not happen like this, right? Why? Why is because, where is it? Right? Why is because your HCl, first of all, is a weak, I would say, weak acid. Okay. Now, what do you mean weak acid? So it will, like, for it to dissociate and give me H plus and Cn minus, it is very difficult, right? First of all, the availability of Cn minus, right? Availability of Cn minus is very less because the acid is a weak acid, so and it will not undergo dissociation that properly. That is one thing. Second thing is Cn minus, even if it is available, right? Cn minus, even if it is available, you will see that Cn minus is a weak nucleophile. Okay, Cn minus is a weak nucleophile, so it will not, even though it is negative alcohol is there, right? It will not be that fast in going and attacking your C double bond, right? So so these two are the reasons why the reaction will not go for 100% completion. Whatever the reactant you have, not all of the reactant would have got converted to the product. Okay, right. Now, next thing what they're asking is, if I have a strong acid, like say if I write HCl in the reference of say some H plus is already there, right? Now, what is going to happen? Right? Now, I think what is going to happen is, right? So, okay, we'll write another thing. Okay, so we have your C double bond O, right? Now, what can happen is if I have a very strong acid, lot of H plus ions will be there. Okay, So first itself, this lone pair on the oxygen will come and take up this H plus. So we will have O, I mean the C double bond O, H, and this will have a positive charge. Okay, right. Now, why are we doing this? Right? Because if this is going to happen, how is it going to help the reaction, or whether it first of all, is it going to help the reaction? Right? All those things we need to understand. Okay. Now, say your Cn minus is coming. Okay. Now, say here we have del 2 plus. Okay, the amount of positive charge, the positive charge on this carbon is del 2 plus. Okay, and say in this case, what I did, like say this one was del 1 plus. Okay, now think about it and tell me del 1 plus will be greater, right? Or del 2 plus will be greater. Think about it and tell me the answer. Del 1 plus is here, normal things, normally how we do it, right? And here we have your del 2 plus, right? So what do you think? Which will be greater? Now, I don't know how you think about it. If I was in your position, this is how I will think about it, right? First of all, why am I even developing a partial positive charge here? It is because the bond is more very polar. The electron density is more towards oxygen, and the electron density is away from carbon. That is why this is having a positive charge. First of all, yes, okay, right. Now, in this case, what is happening? In this case, obviously, this is also a polar bond, but since oxygen is having a positive charge, it is going to pull the electron like very crazy. It is going to pull the electron to a very large extent than in the previous case. In this case, oxygen doesn't have any positive charge, right? It actually has a positive charge now. So it is going to be more and more electron loving. Right, so much of electron will be pulled towards, so we can tell for sure that del 2 plus will be greater than del 1 plus, right? Now, or you can say it like this: in the presence of the acid, this thing is going to happen. This will make the carbonyl carbon more electrophilic, right? This will make the carbon more electrophilic. The amount of positive charge, partial positive in the carbon will be very high compared to the previous case. Now what can happen? This Cn minus will have more attraction for the positive charge. More and more is the positive charge, more and more with the attractive force. Is it not? So the reaction becomes faster. Right? Reaction becomes faster. That is what will happen if I have an acid present. The strong acid is present because the mechanism is going to little change now. First itself H plus will become, right, that will be getting added on the lone pair on the oxygen, so it will happen like this. Then comes your Cn minus, and normally this will happen easily break because oxygen already has a positive charge. It needs so much electron now. So when you break the bond, give it to oxygen, obviously that is the positive is not going to be gone. So what will you have? You will have COH, 2 more bonds, and Cn. The reaction will definitely become faster. Right, and amount of product, say in this case, if you didn't use the strong acid and the reaction went for only 60% completion, right? In this case, the reaction would have at least gone for 75% completion. I'm just giving you some random numbers. All that we need to understand is that the yield of the reaction will increase. The reaction will become faster if I use a strong acid. That is what, that is what I need to answer the question. Very good questions they're asking, right? Okay, right. Okay, fine. Okay, and for this compound C3H6O, we need to write your functional isomers. Let us try to write that. Okay, so we have C3H6O, right? So we can write the aldehyde first, CH3CH2 CHO, or we can write a ketone, CH3 C double bond O CH3. Same molecular formula, different functional groups, functional isomers. Right. So now tell me, this particular reaction, again, both of them are going to undergo this HCN reaction or whatever it is. They're asking you which isomer will react faster. What is the answer? This one or this one? First one or second one? For this particular reaction, which will undergo reaction faster? We saw this, right? Now, how do you decide this? for understanding the reactivity between your aldehydes and ketones, it's all about the amount of positive charge, is it not? So when you have, say, your RCHO, and say when you have your ketone like this, right? Now what we need to understand is this is going to have, say, del 1 positive, this is going to have, say, del 2 positive, right? Now here there is an electron donating group, there will be decrease in the positive charge. Here I have 2 electron donating groups, so there will be double decrease in the positive charge. So obviously wherever I have more positive charge, that is where the reactivity will be higher. So we can always blindly say that aldehydes are going to be more reactive than ketones. One reason is the electronic reason, right? Because the amount of positive is higher in the case of your carbon, aldehydes is carbon-carbon compared to your ketones is carbon-carbon. Second reason is steric reason, right? You have 2 reasons. One is the electronic reason, right? Another one is the steric reason, right? Steric reason is obviously understand, if at all I have a nucleophile coming, right? This nucleophile will find it difficult because there are bulky R groups, which will hinder this nucleophile, this path, and coming and attacking here. But here in this case, I have only 1 hydrogen, right? Obviously, it is going to make it a little more easier for the nucleophile to attack, right? So either way, what will you understand is that this one, the isomer, this isomer will be reacting faster than this isomer. Very, very simple. You really need to work on your organic, very weak, right? You have to work on this. We have seen all these things. At least this question, the other things like, say, this HCN, the other things and all, you don't know, that is okay. But these things you should know, right? How is it that an aldehyde is more reactive than a ketone and all? We have done it so many times, right? Okay. Right, go back, maybe see the videos of aldehydes, ketones, carboxylic acids, then maybe you will get a picture about that. Fine. Okay, next, illustrate the given suitable reaction candidates we have already seen. Okay, now you want to convert your ethanol to 3-hydroxybutanol. Okay, now what we have CH3, CHO, 2, we have CH3, CH, OH, CH2, CHO. This is what we have, right? Okay, you want to convert this into this. Interesting, right? Now, people, please understand, whenever you have increase in the number of carbon atom, here we have 2 carbon atom, here we have 3 carbon atom, the reagent which must come to your mind is, what should be the reagent which should come to your mind the moment you see increase in number of carbon atoms?
HCN.
HCN is a good option. Okay, fine. Other than that, you cannot add, you cannot use HCN for all the reactions. Like, yeah, it is definitely the number of carbon atoms, but only 1 carbon atom will increase, right? What if I need to increase 5 carbon atoms to 6 carbon atoms, 7 carbon atoms? Then what will you do? Like in this case, you need to increase 2 carbon atoms. What is the reagent which should come to our mind? It is Grignard reagent. Is it not that you can have any number of carbon atoms there, right? And you know that minus will attack. We have seen it so many times, right? We will see this. Look at this, right? Ooh, that is we can do. Or look at this, people. Okay, if I write what kind of compound it is, I am seeing it is beta. This is your alpha carbon. This is your beta carbon. Beta hydroxy aldehyde. I have. So what reaction will give me beta hydroxyaldehyde or a ketone?
Sir, aldol.
Yes, this is nothing but aldol condensation, people. You can directly convert this because you're getting beta hydroxyaldehyde, right? We don't have to complicate it. We don't, like, see, 2 carbon atom becoming 6 carbon atoms. You know what is the trick which you have to follow, right? We'll do that. See, we have, say, we will write one double bond duo like this, and we need to take alpha hydrogen, right? So I will write the alpha hydrogen. This is your alpha part, okay? H2, CH, CHO, right? Now we know what we need to do. We need to remove your H2O, right? So we have CH3, CH double bond CH, and CHO. And what I tell you after this, we want to get your hydroxy, this thing. you need to add H2O such that the H2OH minus goes to the beta position, right? So we need to go for CH3, CH, OH, CH2, CHO. This is what we want. That's it, right? What is the reagent which you need to use? It's very simple. All we need to use is dilute NaOH. Done. You'll be able to convert this into this, right? This is a shortcut. How you get it, right? Okay, right? It should strike your mind. See how even I didn't even the question paper, right? But the moment I see this, right? Okay, you can think about, increasing the number of carbon atoms, and then obviously we think of Grignard reagent, right? But OH is there, that too in the beta position, and then we have an aldehyde. Then you should think, okay, this should strike. Definitely, it is going to be aldehyde organization, right? Good, good. The question paper is actually very good question paper. I like the question paper very much because good questions were there. Okay, next, benzaldehyde. I think there is a benzaldehyde 2. Okay, there's a pending mistake. Okay, benzaldehyde 2 benzophenol. Okay, what they're asking here. We have benzaldehyde 2 benzophenol, right? This conversion you need to make. Okay. Now again, what you're seeing that the number of carbon atoms increase, but this time it is not aldehyde condensation. The only way you can think about increasing the number of carbon atoms, one more benzene ring is coming, obviously, when we have Grignard reagent. Okay. So this part has to come from the Grignard reagent. So what can we do? Right? We have your C double bond O H, right? So if I can take your Grignard reagent like this, right? Now this will be the negative charge that will come and attack here. This bond will break, right? So now we would have had, say I'll write C, H, then would have been OH directly I can write, is it not? Because this O minus will come, OMGBr will come, and then I go for hydrolysis, this will happen, right? And then here I have a benzene ring, right? And then here also I have one benzene ring. Right. Now, this is not the end product. We have an alcohol. How do you convert this into this? Obviously, we need to go for oxidation, right? You can go for either PCC or you can go for KMnO4 to convert the secondary alcohol into your aldehyde, ketone, right? First step is MgBr, and then obviously you have to go for hydrolysis, right? So that you'll get a OH here, and then you have to convert this into your ketone by adding an oxidizing agent like this. Very, very simple. The moment you see increase in number of carbon, I told you the first thing you should strike is your Grignard reagent, right? Okay, that's about this question. Next, write one chemical reaction to exemplify the following. Rosen conduction we already saw. It was already asked in the question. Tollens reagent, we know what happens here. Tollens reagent is RCHO, right? We can write Ag NH3 twice plus. This is your ammoniacal silver nitrate, you call it, right? This is your complex, which will be getting in the Tollens reagent. And we know it is a mild oxidizing agent, which will convert your this thing to RCO4 minus, and Ag will be precipitated, silver mirror. But instead of R, you need to take a proper example, say CH3CH or something like that you take, and then do this, right? Ag will be precipitated. Very, very simple. Silver mirror is what is going to get formed. Okay, right? Next, okay, this is not in the syllabus because it comes under Faraday's laws of electrolysis, right? So only have to answer this question. Even if you didn't answer this question, you would have been given marks. Okay, at least we'll tell that to whoever corrects the paper, right? So this is not in the syllabus. Okay, electrochemical equivalent comes under Faraday's laws of electrolysis, which is not there in the syllabus. Okay, next one is very easy. Calculate the cell EMF and delta G naught. Right, you have to see be very careful. They're asking you delta G naught, not your delta G, right? We have an equation like this: delta G naught is equal to minus NF E naught cell, and we have delta G is equal to minus NF E cell, right? If I have standard Gibbs free energy, right, then we take a standard cell potential. If I have non-standard Gibbs free energy, we take the non-standard cell potential. In this case, they're asking you delta G naught. So you have to use this equation, right? And this E naught cell can be directly calculated, is it not? Right? E naught cell, how do you calculate? Will be equal to E naught of cathode minus E naught of anode. You already know this equation, right? So what is cathode here? Obviously from this thing itself you can understand, right? Zinc This one is going to act as anode because cell representation. We always write the anode part first, double bar, then we write the cathode. Right? Fine. So they have given the reduction potential for zinc is this much. So now you can easily write this. Okay, so this is nothing but E naught Cu2 plus bar Cu. You always take only the reduction potential. So you always write only the reduction like this. Minus E naught of Zn2 plus bar Zn. Right? This is your reduction potential for zinc. This is your reduction potential for copper. So what we have minus 0.763, minus of minus 0.403 something. So you know what is your E naught cell value. Very, very simple. I think this shouldn't be minus. I don't know why they gave this value. It should be plus. Okay, right. And then eventually you will be getting some answer as 1 point something. You will be getting, you can calculate and do this. Okay, that is what is your E naught cell. Right. The moment you know the E naught cell, then we know that delta G naught is equal to minus NF E naught, right? F, you know what is the value? F value is 96,500, right? What is N? N is the number of moles of electrons, right? N is the number of moles of electrons. Now, how do you calculate this? We need to go for the overall reaction, right? Now, what is happening at anode? Anode, we know oxidation should happen. Right, so zinc will be getting converted into zinc 2 plus by losing 2 electrons. Okay, now at anode, at cathode, we know reduction should happen. Right, so what is going to happen here? Cu2 plus accepts 2 electrons to form copper. Right, now in this case, whenever we write the overall reaction, right, what we need to remember in overall reaction, no electron should be there. Right. In this case, they'll directly cancel out. Right. 2 electron will directly cancel out. So overall reaction would be zinc plus copper 2 plus giving zinc 2 plus copper. Right. In this case, they're directly canceling out. But what if I had 2 electrons here and 3 electrons here? Right. At that time, you would have multiplied. This should be multiplied by 3. This should be multiplied by 2. So overall, you will be canceling 6 electrons. That will only get cancelled. Right. So in that case, N value would have been 6. Whatever is the number of electron you cancel to write the overall reaction, that is your N value. In this case, what you're cancelling is 2 electron. So for this case, N is equal to 2. Right. In this case, N is equal to 2. So you can write delta G naught is equal to minus 2 into 96,500 into 1 point something, whatever you got, that you can put it here and then find the answer to this delta G naught. Okay. Right. Now, they are asking what is cell potential. For that, we use the non-state equation. We know E cell is equal to N into log of QC. This is your equation. Again, why 0.059? Whether they have given the temperature, I think they have not given the temperature, have they? Okay, 25 degrees Celsius. Whenever it is 25 degrees Celsius, we know that we have to use this equation. Right. Okay. Now, what is QC? QC we know is nothing but your reaction quotient. Right. Now here this you take QC from the overall reaction. Here we have zinc solid, copper solid. This is what is the concentrations of Cu2 plus tau they have given, right? Concentration of Cu2 plus is 0.01, Zn2 plus is 0.1. You can see. Right. Okay. So from the overall reaction, for this reaction, if I write the QC value, right, we don't take solids, right? We have to take only the aqueous solutions. This is aqueous solution. This is aqueous solution. So all that we have is concentration of Zn2 plus. Now remember that if at all I have any stoichiometric coefficient, that has to go to the power. In this case, it is 1 because all of them are 1, 1, 1, 1. But if at all I had say 2, 3 or something, that should go to the power. Be very careful with this. Okay, fine. Zn2 plus divided by Cu2 plus concentration. That's all we have. So you can find the QC, it is 0.01 divided by 0.1, right? Now, if at all you're getting confused of how to do this, we have 10 to the power minus 2 divided by 10 to the power minus 1. So all that we have is 10 to the power minus 1, which is nothing but 0.1. Okay, or you can keep it as 10 to the power minus 1 only for easy log calculations, right? So you can find it here, E naught cell, some 1 point something value, 0.059, and we know we have to calculate what are the number of electrons cancelled. That is what you need to take. So this is 2 log of 10 to the power minus 1. That's it. You have to, you can bring this minus this side. So we have 1 point something plus, because this minus will go here, minus will get plus. So we have 0.059 divided by 2 into log of 10, and I know log of 10 value is 1. Okay, that's it. So 1 point something plus 0.059 by 2 is what is your answer. This is your answer to the question. Very, very simple. Right? See, this question is very easy because you didn't multiply by anything. There was nothing coming in the power. You don't have to multiply and then cancel, right? But if at all that kind of question comes, please be very careful. The number of electrons, whatever you cancel to get the overall reaction, that is your n value, right? And be very careful with the QC. You need to put something in the power if there is any stoichiometric coefficient. In this case, all are ones. But if at all there are 2, 3 or something, that power should come in the numerator denominator. Be very careful with this. Okay, right? So yes, that's about this paper, right? Anybody has any questions? Okay, right? So I think we are done, right? I think we can go. Thank you so much, people. We'll meet again next week.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.